Hey everybody, I want to give you some help with this pivot interactive in case you're having trouble. Um, most of it's pretty straightforward. They show you how they got the graphite out of there, and then, but a little bit was just like measuring. One thing I noticed that's a little tricky is if you overlay that ruler, I'm just going to pause the video here. When you overlay that ruler, you want to make sure you're really going from inside edge of the one device to the inside edge of the other device, and also make sure you're playing the video for that first question to the very first time that they play it. So if I need to go back, just back up the video. But you see what that's going to do, it's going to go from like this side here, the inside edge of that metal clamp, to that inside edge of the metal clamp there. That's the distance that they're looking for. And they give it to you in centimeters, and kind of the annoying part about this, if I would have taken more time, I could edit every single question and choice that left it in centimeters, but instead I'm just going to leave it. Ideally we'd always just convert to meters right away, but they have you convert in the very last step in meters. So they even want you to graph in centimeters, which is fine. Leave it in centimeters. If it was a physics lab, we would have just converted it right away. And all these questions should be pertaining to then it being left in centimeters until we get down to number, let's see, I think it's, yeah, number 10. And this is where like the real lesson comes in number 10 is this concept of resistivity. The symbol for that is rho. And so rho is that little Greek letter. It's also, we use it for density in different contexts, but rho is the idea of resistivity, and every single metal has its own resistivity. Copper has a different resistivity than gold, and certain ones are better than others at conducting electrons across them. And so we want to pick materials that actually have a really, really low resistivity. That way it would make the resistance a lot lower. With low resistance, you can conduct the electricity better without causing heat to build up. So here's the full equation of how electrical resistance works, and this is how it's defined actually on the properties of the material. The length of the conductor, so imagine this Apple Pencil is my conductor. The length that I'm using would be that resistance. If you do like the wire of a thing of headphones, the longer the wire, the more resistance that's going to have. And so for best electrical conduction, you should have a really short wire. But then that's not always convenient. It's nicer to have a really long wire to connect to a wall so that you can route the electricity to where you want it. But when you do that, you have to kind of bump up the voltage so that you can keep sending the correct amount of charge to the device. So length has a direct impact. The longer the wire, the more resistance you have. Cross-sectional area would be like, okay, so if my wire is a cylinder and you turn it on end, I don't know if this is lined up perfect. Let me see. I can check my camera. But yeah, you get a circle. So what they're doing is the cross-sectional area would be like if you slice that wire, you would get a perfect circle, and then you can calculate the area of that circle with just pi r squared. So this is where some of the conversions and the math would come into play, and I'm going to cut over to an explain everything file just to show you that idea. All right, so if you took a long wire and sliced it, let's say on end like that, and took a look, what you'd actually see is a circle. If we zoomed in and kind of looked at a cross-sectional part of this wire. And so what they did is they gave you a diameter, but they annoyingly gave it to you in millimeters. And so, step one of this to get everything into standard units is we're going to have to get everything into meters. So, first of all, that diameter you want to cut in half to get the radius. And then once you get the radius in meters, then you can go ahead and solve for the area. Keep in mind, area of a circle equals pi r squared. And I would convert that radius into meters first before you do that math. All right, next, the slope that you got, the slope from your graph here of resistance and length was really the resistivity over the area. but that was in centimeters. And so let's say you got a value of like 0.85. That'd be ohms per centimeter. What you have to do is convert that into meters. And so, like, normally we move our decimal over 2 places to the left, but because you're dividing, we actually move our decimal 2 places to the right. And so 0.85 ohms per centimeter would really be 85 ohms per meter. So that value you can go ahead and plug in for your slope once you convert it to meters, and then you just solve for the area, and that leaves just your resistivity to solve for, and that should get you that last answer. So just some conversions on there I wanted to help you with, but that should take care of it. All right, so I hope that was helpful for you, and we'll check back in on Google Chat or just on Google Classroom if you have questions. See you later.